part of 3.2 is the empirical rule. And the empirical rule is really an estimate, okay? So just in general, if we have this normal bell-shaped curve, so notice it's only for bell-shaped, and that's going to be your key word when you work on My Math Lab. They'll have a problem and they'll be like, blah, 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 assume the graph is bell-shaped. And that's kind of your hint, like, oh, I need to use the empirical rule, okay? So bell-shaped means use that empirical rule. The other name for it is 68, 95, 99, 7 rule. I don't know, I guess you can remember that. But this right here, what's typed this way, is what you're actually going to have on your formula sheet. So you don't actually have to memorize those units. You just need to know what it means. So if a distribution is roughly bell-shaped, then approximately 68% of the data will lie within one standard deviation of the mean. So notice this is just mathematically showing you this. What does mu stand for? The mean. What does plus or minus mean? Plus or minus. And what does sigma mean? The standard deviation. So this is physically showing you the means in the middle, give or take a standard deviation. 68% of our data. What does that mean? It means if we have this curve and it represents all of our data, 68% is within one standard deviation. Take it a step further and go 2 standard deviations out. So approximately 95% of the data lies within 2 standard deviations. So go an extra standard deviation out, guys. There's 95% of your data, which is crazy. That's almost all of your data is within 2 standard deviations of your mean. And then take it one step further. 99.7% of your data, basically 100% of your data, is going to lie within 3 standard deviations. Just a little note, you can use the empirical rule with sample data. You would just use X bar for the mean in the middle, right? Instead of plus or minus mu, you would just do plus or minus S. So it's just using the same symbol, or the same idea, but you're using the correct symbols for standard deviation and so forth, okay? So that whole thing could be rewritten using X bar as your mu and S as your deviation. All right, so how are they going to ask you questions on My Math Lab? They're going to give you a scenario where they will always tell you the mean and standard deviation. And what we're going to do is we are going to play around. I give you this guy, okay? So I will have this written. I will also give you this on the specific problem, okay? So you don't have to memorize it. You just need to be able to manipulate it, all right, based on your specific problem. Because every problem that's roughly bell-shaped will use this exact same measurement with the exact same percentages. The only thing that's going to change is your x-axis. The mean will differ depending on, the mean number of basketball points you score compared to soccer points you score is going to be different, right? You might score 20 points in a basketball game. You're probably not scoring 20 points in a soccer game, right? So your mean will differ and your standard deviation will differ. So this x-axis down here is really the only thing that changes. What's going on? They're just splitting it in half. Remember, bell-shaped was symmetric, which means it's just the same on either side. So if 68% of your data lies within one standard deviation, what's half of 68? 34. And that's all they're doing there, okay? 95% was half of 95%, 47.5. But we've already labeled 34%, so that 13.5 is the other part of 47.5, and so forth. The very little outskirts are just the remaining 0.3%, right? If there's 0.3% and 2 tails, 0.15 is on either side. So all they're doing is taking these percentages and splitting them into chunks based on standard deviations, okay? So let's see what's going on. There's an SAT math score that has a bell-shaped distribution with a mean of 515 and a standard deviation of 114. Before I even read these problems, I see bell-shaped, so I know I'm going to use the empirical rule. If I'm going to use the empirical rule, I am going to draw my own little empirical curve, all right? I won't get as picky as like labeling the 34, 13 and stuff, but I am going to label my x-axis on what is the mean that goes in the middle and what happens when I add my standard deviation a couple times and what happens when I subtract my standard deviation a couple times. So what was the average on this SAT math test? 15, right? So that's going to go right in the middle. And then what is the right side? I go in one direction just because you just add, okay? Notice the right side, you add one standard deviation, then you add another, and then you add another, okay? So if we have a standard deviation of 114, our next tick mark, if we add it, will be what, 629? Is that right, the right math? And all I did, guys, was add my 114 there. That's 629. Add another 114. Where does that get you? 743. Add another 114. Where is that going to get you? 857. Is that right? Does everybody see what I did there? I'm just starting with my mean in the middle, and I'm adding my standard deviation 3 times. So I'm going 3 standard deviations out to the right. How am I going to do the left side? The same thing, but just keep subtracting 114, okay? So 515 minus 114, is that going to put me at 401? Is that right? Minus 114, what's that going to put you at? 287. And then one more time, guys, just always go 3. That will be what? 173. And the whole idea here is I now have this stuff labeled. So depending on what chunks I'm looking at, that's the percentages I'll pull from this chart, okay? This chart is consistent. It's always 34, 13.5, 2.35, and 0.15, okay? What's going to change is your x-axis, which we now have our new x-axis, all right? So let's go ahead and look at the question. The question says, what percentage of SAT scores is between 401 and 629? 401 and 629. 68%. How'd you know that? Because 401 was 1 standard deviation to the left. 629 was 1 standard deviation to the right. We're just adding those 2 middle columns, which was what? 68%. Okay? So however you need to show that, this is technically this. Right? That's technically that. Our mean plus or minus our sigma. I like to just show it as that it's the 34% plus the 34%. That's going to give us 68%. So this is within 1 standard deviation. So this is the technical, mu plus or minus sigma is the technical notation within 1 standard deviation of the mean. But since we labeled our generic empirical rule over there, we know that we just went 1 standard deviation to the left because that's where 401 was. We went 1 standard deviation to the right because that's where 629 was. So that's here on this chart. So that's the 34 and the 34, or the 68%. B is going to be really similar. What percentage of SAT scores is less than 401? Less than 401 and greater than 629. Couple ways to do that one. What percent is less than 401 and greater than 629? Anybody brave enough to say the answer? What is it? 32%. Okay. A couple different ways. How did you figure it out? Okay, so I think that's the easy way. So you guys know if there's a 68% chance of rain today, there's a 32% chance it's not going to rain today, right? So if 68% of your data lies within those 2 amounts, then 32% lies outside of it. Say you're not as nifty and you don't see that, guess what you can do? You can add this chunk, and this chunk, and you get 16%, but guess what? This plus this, 16 and 16, okay? So you can do it one of 2 ways. I would do it exactly like Spencer and just do the 100 minus the 68%. So outside 1 standard deviation. Okay? Outside 1 standard deviation. Or we can add, what's that going to be? 13.5% plus 2.35% plus 0.15% and get 16% in 1 tail. So times 2 is 32% and 2 tails. Okay? So either way you do it, just make sure one way or the other makes sense, okay? This is called something that we don't learn until chapter 5. It's called the complement, which means opposite, okay? What's the opposite of being within the 1 standard deviation? Being outside 1 standard deviation. So if we have 100% of our data and 68% is inside, there's 32% on the outside. If you're like this, where you just like that strategic, you like to use this map chunk for chunk, that would work as well. Just add up each individual segment to see how much is in one tail, and you'll get 16%. Double it because you have 2 tails, and you'll get that 32%. Last but not least, what percent of SAT scores is greater than 743? So notice that's this right here. So that is what? 1, 2 standard deviations out, is that right? So we'll go 1, 2 standard deviations out. That's just equivalent to these 2 little chunks up here. So what are you guys going to get there? You're going to add 2.35% plus 0.15%. Do you guys get 2.5% when you do that? Okay. Another way to look at it is kind of the same way Spencer did the part B. If it's the tail, it's the opposite of 2 standard deviations out. Well, we know 95% lives in the middle, so 5% lives on the outside. So how much is in one tail? 2.5%. So again, however you need to see it. I know some people can just look at it and know. Other people are just like, nope, she's going to give me that. I'm going to label my axis with my new numbers, and I'm going to go from there. Okay? Either way, are you guys okay? Are you seeing where those numbers are coming from? This does not need to be memorized on the exam. I will give you this generic one on that specific problem, and then you label it with your mean and your standard deviation to get that new x-axis.